So I'm going to talk to you about safety critical component verification using leveraging formal techniques. Really, most of the presentation is applicable to many applications. There are some examples here which are more specific to really safety critical components, but I think it's a good field to show where the pressure to get high quality and keep the cost down is such that the formal really becomes even more needed. So yeah, I mean, obviously in safety critical application it is important to achieve your certification. Ultimately, you want to avoid even possibly catastrophic events, and you don't want to make bad news, which can impact business, can impact your credibility, and can even lead to prosecution. Now, the problem with the safety critical application is that on one side you have more complex chips going in, so obviously more chances for human errors. On the other side, you also have smaller geometries, which means that random failures are more likely. So if you have a smaller geometry RAM, for instance, it requires less energy, for instance, for an alpha particle to hit your chip and flip a bit and create a random failure in the field. So you really have two forces working against you, more complexity and smaller geometry. And so from this point of view, there is higher chances of failures. And since 2006, the market has become more and more aware of functional safety standards, and some requirements have shifted, and now component vendors have a really active role in ensuring safety by design. This really works mainly into different areas. On one side, improving your processes to ensure that there is less chance to introduce errors. And on the other side, introducing logic in your design that is meant to deal with failures, detect failures, possibly correct failures, and propagate information on failures to parts of the design that are supposed to deal with it, and possibly, for instance, bring your system in a safe state so that at least nothing catastrophic happens. Here's a picture on the safety standards. So there are several standards, depending on the industry. I think the DO254 for aerospace and defense is the US. Then under the umbrella of IEC 61508, there are several industry-specific standards. Probably one more familiar one probably is the automotive one, 26262. And yeah, obviously it is essential to comply with these standards, first of all, to actually minimize the risk of harm to people. And then, obviously, there are business reasons, and as I said, even the risk of prosecution. And for instance, if you think about the automotive market, where the life cycle of the car is quite long, and some of the revenue could end up being prosecuted for a chip that has been developed quite a few years before. So. If we look at the general flow for safety critical application, we have the familiar steps of planning, requirements, conceptual design, detailed design, and implementation. Then at every phase, really, there is the possibility of introducing error. So obviously, random errors, for instance, an alpha particle hitting your chip and flipping a bit, this happens in the field. And probably nowadays, products have functionality also to deal with this situation, and this safety function needs to be tracked to the complete flow. Make sure they are also correctly implemented, so verified. And then there are also systematic failures that can be introduced at each step. An example, for instance, here could be a bug in your synthesis tool that introduces a systematic failure in your chip. And also, it's equally important to safeguard against this type of failure. And this is really generic. So on the implementation side, then the next step could be actually programming an FPGA device or generating masks for an ASIC. This is quite interesting because there is a quote from the United States Nuclear Regulatory Commission effectively encouraging the use of the advanced techniques such as formal verification together with code coverage, and this specifically refers to the verification of safety critical FPGA design. And really it's also interesting to say it should be an integral part of the design life cycle. So I think it's quite interesting how there is here a quite explicit push for a specific type of technology to be used. And yeah, I mean, here it comes a bit of the OneSpin message. We can help in this. So many of the things that we provide a general purpose solution that find a natural applicability to safety critical component verifications. And some example we will see maybe are more specific to really the safety critical world. But yeah, now we will look at some examples. Probably I will not go through all of them. Preventing synthesis bug. So this is the example I mentioned before, and you might have a systematic failure introducing by the synthesis tool during implementation. For example, a wrong sequential optimization that leads to reading an outdated value from an FPGA flop. What is the solution here? The solution is OneSpin has a solution for this. It has an equivalency check for FPGA that is able to formally prove the equivalence between your RTL and the output of the FPGA synthesis tool, and make sure you don't have this problem. Now, what is some more information on the added value of this? So the problem with conventional equivalency is that they do not support advanced FPGA optimization, and they might require more extensive model intervention. An FPGA typically you want to be fast in running your flow, and they rely on synthesis side file. So the synthesis tool perform the synthesis and maybe create some side files to help the equivalency checking tool. But then really the whole point of equivalency checking is to be independent from the synthesis tool, because you don't want the synthesis tool to guide the equivalency checking to make the same mistake you made, and then they just say green light, but actually there is a problem. So one of the points of equivalency checking is really to have an independent check on the synthesis. And OneSpin 360 EC FPGA, which is really a unique tool in this space, address these challenges. An important thing is that is able to handle FPGA, all the FPGA specific optimization, because obviously you can also make the life of the equivalency checking tool easy if you just don't use the optimization. So if you just drive the synthesis tool to not do fancy things. But obviously on the other hand, to meet your targets, you want to push the synthesis tool to use the optimizations. And the equivalency checking tool is able to handle this optimization. It relies on sequential algorithm, more advanced equivalence checking algorithm to actually manage to prove equivalence. It's able to work on the old chip, on the swap netlist as is, doesn't need the hint files from synthesis, is completely independent, and is a highly automated flow. So effectively we have a flow, a number of flows that are set up for the specific platform you use, so it's very quick to run the equivalency check. Now we go on a different word, on RTL verification. So there are, as we saw, for instance, in the phase of detailed execution of the project, where actually you code your RTL, there is a possibility of introducing bugs, of course. and these bugs introduced by human in this case, or before we saw an example of a bug introduced by a synthesis tool. Here's a bug introduced by a person, and this could cause a systematic failure. For instance, a simple example, an RTL designer putting a synopsis full case pragma there, and this is actually wrong, so this will wrongly guide the synthesis tool, and effectively what is synthesized could have a bug that is not spotted at the level. And obviously there are many tools that can check this kind of problems, but what we see is that conventional link checkers require a lot of setup, and the other problem that we see is that they might report a large number of issues. So OneSpin tool, which is called OneSpin 360dB, inspect the strength really are, in this case, the easy setup and flow integration. And the other major point is to use the formal engine to actually find only the real issues, or in the case, proving that things are fine, or really pinpointing the real issue and bringing up actual traces to quickly debug these real issues. And it's really highly automated, and it's applicable on the early RTL. So you don't need the test bench. As soon as you have some RTL, you can run 360dB inspect and detect a large number of issues, or, on the other hand, make sure that all these issues are flushed out and you don't have this kind of systematic failure. Another application here is, so another problem could be that you have to achieve your certificate specification is actually code coverage. So for instance, in the case of DO254, there is a part of this which is called elemental analysis, and actually what ends up is that if you have an insufficient code coverage, you might not get the certification. And sometimes it's quite difficult to for a designer to waive some code that is not covered as, okay, this is uncoverable. So this is a solution that now is widely available really in the industry, and is formal to automatically detect that code, even in complex situations, which is obviously more productive on one side, because it's an automated process that can either prove that a certain line of code is dead, so the designer's verification doesn't need to bang his head trying to hit that line, or try to go through some complicated analysis to waive it. No, this is unreachable. The tool can do it automatically. Or on the other case where you can actually hit this line, the tool can provide you information, so effectively a trace that shows you how to cover that specific line. And this is again of great help, for instance, in this case, to achieve certification timely. On a little bit on the so far we looked really at the fully automated push button solution that can bring the power of formal into into your flow, and in the specific examples to speed up and ensure your path to certification. A little bit on the going a bit on the higher hand. So obviously you can have also human failures that are introduced again during the design phase, RTL bugs effectively, and in this case to verify a vital part of the design, one can use assertions to express in a much more compact way, much more powerful way, what the specific critical expectation is. Here is an example of, for instance, two signals that needs to be mutually exclusive, which is a very simple thing to express, but the power of formal verification here comes in the sense that if there are deep corner cases where this signal will not be mutually exclusive, the tool will automatically find it. So you're not relying on your input stimuli, on your test bench to create the right scenario to hopefully expose the bug, but the formal will do it for you. So again, in the verification, and we have customers doing this for the verification of the vital function of the design. This is, I would say, it's a must in a sense, because you just cannot get this with simulation. A different, yet another different scenario. So another place where you can introduce problem is at the specification level, really, where you actually forget to specify something. Here's an example where maybe you specify the case where you have no gas, no brake, or you hit the gas, but you are not hitting the brake pedal. You hit the brake, but not the gas. So, and then you say what your system needs to do. But here there is a systematic failure that is really introduced during this conceptual phase, because you are really not describing what the scenario when you hit both the brake and the gas at the same time, which is something that can happen. Maybe you think it's not sensible, but actually can happen. Someone might do that, and you forget to specify that, and people forgets about it, and then actually maybe it happens then when you hit both, the gas takes priority, and that you don't really want to happen, and that could be really a systematic failure introduced at the conceptual level. And obviously there are various ways to catch this. One thing is a review. You probably have some people reviewing, someone can spot this problem, but you are relying on humans, and also it's an inefficient process. With another, so we saw 360 dB inspect from OneSpin to do all the automated checks. We saw 360 dB verify, where the user writes assertions or deal with some assertion to, for instance, prove critical part of the design. And there is the third family of group of tools from OneSpin, which is 360 dB certify. And in this case, the user, which is really in this case is expert users, describing the operation of the system into high-level assertions. And then there is a tool that automatically analyzes this and effectively detects if there are scenarios that you haven't specified. So it kind of spots this. But yeah, I mean, I want to also stress the fact that we have customers doing this, so it's real. It's done for a long time actually, but it does require through planning and also execution by trained personnel. Yeah, another example here on safeguarding memory. So in this case, for instance, you might have the problem, as I said, of an alpha particle hitting the memory and flipping a bit and causing an error, and then you want to really, you have logic encoders, decoders, redundancy bit in the memory to detect and possibly automatically correct these issues. And again, to verify this part of the logic, error correcting codes, formal is very powerful. You don't need knowledge of the ACC algorithm. It's very easy to inject faults and actually verify a huge number of combinations of potential faults, and ultimately do an exhaustive verification here that is totally impossible to do by simulation. And this is, for instance, also a case where formal can quite cleanly replace simulation. So you can say, going back to Mike's question, sometimes it's hard to say, okay, I'm doing this formal work, what can I skip from simulation and save effort? This is an example of safeguarding register. This is more specific to actual safety critical verification, and there is some redundancy here introduced to deal with the potential errors on registers, and there are various techniques to do this, but ultimately there is logic in your RTL that needs to detect if there is a fault, and which can also be a transient fault, not necessarily a static fault, and then needs to detect this and maybe propagate the information to a safe management unit that needs to deal with it. And our tool has very good capabilities to deal with this. In particular, actually, the easy way to insert and handle large number of faults, various clusters of faults simultaneously, and effectively achieve a level of verification that you wouldn't be able to do in a lifetime with simulation. And yeah, I mean, the other thing is that actually we're able also to work on the netlist level with this. Not only on the RTL level, but also on the netlist level. because, for instance, the ISO 26262 demands that safety features are verified at the netlist level to achieve ACD level compliance. There is another example here, which perhaps is my last one, where you need to, we have seen just before this problem of quantifying the coverage that you achieve with your formal assertions, and hopefully also leveraging this and achieve your overall sign-off that you get from simulation, verification and formal. And so in this specific case, there is a problem also qualifying your verification environment for safety functions. OneSpin has a specific tool in this arena. We are able to compute coverage for your assertions. We have taken maybe a different view from others. We like the idea of bringing to the users something that they are familiar with and that can be easily merged with your simulation results. And we went through the line of having actually structural coverage for your assertion. So we have a tool called Quantify that computes the coverage of your assertion that is reported in a very intuitive way in a HTML report, which obviously has your summary metrics for management to see your progress, how much you've covered, how much you have not covered, but also actually having a color annotated version of the RTL to see the part of code that you have covered, the part of code that you have not covered, and which is very intuitive for the users. We do observation coverage, so this is a little bit more than what you're using in simulation, because in simulation you just need to execute a line, say, okay, I've covered this line, doesn't mean you really have any checker that will spot the bug on that line. We also do this, so we have the concept of observation coverage, which goes a little beyond the normal structural coverage, and the goal of this is really not only this assertion kind of execute these lines, but this assertion really checking this line, and if there's a bug in this line, it must be caught. And the other, so on one side, this really helps novice users also to guide their work to see, if they are covering what they expect with the assertion they write. But also, the other advantage that we see in this is that it can easily be matched with your simulation results. So as a matter of fact, we are working with TVS, with the tool SureSign, and well, basically they are able to pull in results from simulators, from code coverage, and also results from our tool, from formal, and merge the results and really have sort of a flow that leverage both efforts to achieve the sign-off. So yeah, this is the last point here. We can easily layer the results of this tool, Quantify, into the simulation-based flow. And I think I have another slide on this. So yeah, I mean, I think why this matters to you, because obviously you want to improve design process quality, particularly for people doing the safety critical application to achieve certification, but I think it's of interest to anyone. And the other important things that you don't need to hold back on innovative tool developments, advanced options. We made the example of CFPGA, where users can really take advantage of the synthesis tool, use advanced optimizations, and still have the ability to verify them with an independent tool. And yeah, I mean, the use of our formal verification solution in this specific context increase the quality and really speed up and secures your process to achieve certification. So I also invite you to, for whoever goes to DAC, we have a more detailed story on real application on this at the designer track. And yeah, I conclude this here.
Thank you very much, Sergio. Does the invitation include the flight? I'll just...
we may put you in contact with a good travel agency.
Okay, thank you. Is there any questions for Sergio?
It's Isidoro Sorbello from Infineon. So it's more a question about Quantify. So it looked to me that from a point of view of code coverage, let's say we are really nowadays able to merge the result from simulation and formal activity and to avoid to repeat the effort. There is any plan and idea for functional coverage? I don't know if the tool could read functional coverage written in SVA, PSL. Theoretically, it could check as well if that assertion is hitting code coverage, is covering as well, is hitting the coverage, functional coverage point, and that will cover the latter part of the matrix, and so everybody will be happy.
Well, yes, this is possible today if you express the functional coverage point into SVA or PSL. Obviously, the problem is that a lot of people, as the coverage expressed in, for instance, UVM or in Specman, and with classes, and we are not able to read this kind of language yet and see if the assertion is covering this. But if you have a functional coverage model in PSL or in SVA, this is possible. Yeah. The problem, we cannot read the UVM, so to speak.
Okay, but it's interesting. So yes. PSL, SVA
yes.
already is supported. So we actually could write already the a product matching full functional code coverage.
Yes, yes, absolutely. I mean, the other thing I want to stress, I don't know if it was clear, that this is also unique technology for OneSpin. So the ability to merge the coverage, to derive structural coverage results from the assertion, being able to match with the simulation is unique. But we are not yet able to read UVM.
Tom Lake from Interglossa. Just to ask, are you saying this is all fully automatic, or are you offering any interactive? I didn't understand whether there are any interactive facilities here.
Quantify is fully automatic, so actually it can work with assertion written in PSL, SPA, even OVL. You might have another tool proving your assertion, for instance. Then Quantify is fully automatic. It reads your RTL, it reads your assertions, and it's a push-button tool, and will come up with this report which has the summary metrics, how much you're covered, how much you're not covered, if some code is dead, if some code is not covered because of constraints, so I didn't go into the details, and then annotates your RTL with color coding. Okay, this line is dead because it's unreachable, this line is not covered because of your constraints, this line you have observed, this line is not covered. It's very easy to, and you can generate UCDP database out of this XML exchange format.
Emiliano Morini, Imagination Technologies. You said that you are using error correcting code to check random faults. And how are you sure that introducing redundancy, you are not introducing the same problem in the redundancy that you are introducing?
So, first of all, our customers use error correction code logic. We provide the tool to verify that. So, basically, the point is that, for instance, if you have, I don't know, single error detection and correction, you want to do insert faults and make sure that the output of your logic is correct, so that you have detected it, and if there is correction enabled, it's correct. So you can effectively write a session to express this and formally prove it, and the tool has the ability also to insert faults, and you can if you can exhaustively prove that if you, for instance, insert a single error, this will always be detected, and if there is correction enabled, is correct. So our customers do that. Then you can do other things, put an encoder, decoder together to make sure they work correctly together, and yeah, this is much more powerful than simulation.
Thank you very much, Sergio.
Thank you.